yeah, oh yeah, maybe you should check it again, but I'm quite sure it is. Just check. Yeah. F5.
I'll start. Yeah. Okay. Hello everyone. My name is Piotr-Lewkowicz. With Igo and Jay, I want to share with you our experience with the summer school in the Alpbach, and we're going to present you also the mission which we designed. So summer school in Alpbach, 2012. In the front of the page you have all participants from the summer 2012. Okay. Okay. So the school has long, deep history. Already 55 years of tradition to teach in the space, technology and science. Each year is usually 60 students from all Europe. Also, this takes 10 days. We are working the Alpbach, Austrian, in the Alpbach. It's the beautiful village in the mountain in Austria. And the lectures, they are from all world. In this year, we have the pleasure to see the presentation of the John Cassani. He is the former head project management of the missions like Voyager, Galileo, and Cassini. And this year, the topic of the summer school was the exploration of the giant planet and their system. So now, quick review of the summer school program. Almost every day there are lectures, and the usual relevant of the topic of the project. For this summer school, it was also about the giant planet and the system, about Uranus, Neptune, Jupiter, and Saturn. Also about the scientific requirements and quick review about the mission, the previous mission, like Voyager. So, ever the most exciting lecture are usually very exhausted. So, for all participants are coffee break with the free tea and coffee, and it's a great opportunity to talk with our tutor about what we didn't understand during our lecture. I talk with them all the time. After that, yeah, probably the most important part, the workshop. It's after the second day, 60 students are divided in the 4 teams, and each team has to design the mission from the very beginning. They have to include the cost, the scientist requirements, the engineering solution, everything what is relevant there. Each team has his own, they have own scientific and engineering tutor. In the end of the workshop, every team presents their work to the front of all participants, and they are judged by the independent jury. So every day during dinner, each team presents their daily report. They ask them, the tutor asks them what they did and what is going to be next step. Also, it's great time for the students because we eat our dinner with the tutors, and it's the really nice atmosphere that you can eat with your tutor, talk with them about everything, and it's going. Yeah, okay. Sorry. After dinner, all participants came back to the school and still doing their project. Probably maybe not the most important part, but also very interesting. Every week we finish our work really late. Our group spend all the time together, And I think it was really great that we did a great job. Still, we did eat lunch together, go to bar together, and because of that, we really know each other, and our work was so cool. Yeah, okay. Every year, sorry, all in the traditional summer school in Alpbach is taking the hiking, and we have reached the top of the mountain, and there's traditional photo. They're almost all participants of the summer school. And maybe much more formal, the summer school objective. So, motivating participants into space technology and scientists, working in the international team. It's like those kind of, for me, really tough. Was my first time when I collaborate with the scientists, and I didn't really realize what they're doing until when our team was awarded for the scientist case. And yeah, working in the teams and develop the professional network and enjoy Alpbach experience. And now just Alpbach experience, it's really informal that you can speak with all tutors, because they have their opinion about your project, what you can do in the future. They give me many advice what I should do in the next step in my career. Yeah, less tutors that you can imagine. There was many tutors from all over the world, like the John Kasani. Yeah, the novice learn from the expert learn from the novice, and interaction between scientists and engineering. So what I mentioned before, like we see here. And yeah, sometimes too much pressure. So now I give the Afjai to represent the scientist case of our mission.
Hi, so the theme for the summer school, the year we did it, was a mission to the outer planets. But there was a strong influence on pushing us towards the icy giants Uranus and Neptune, because there's very few missions currently planned for them, or the ones that have been planned haven't been manifested. So we came to a group decision that we'd explore Uranus for various features I'll be going through, and our mission statement came together to study the Uranus system, to give crucial answers about its current state and evolution, to investigate some of its unusual features like its strange inclination of both magnetic and gravitational field. We also decided, due to the scientific things we wanted to prove, that we'd end up flying 2 satellites. We'd have a slave satellite, so we could take 2-point measurements of the magnetic field. So we started from what do we know about Uranus. We've got the facts from the Voyager 2 flyby, and we also have some observations from ground and Earth-based telescopes. Some of the big questions that Voyager raised was that it had unusually high winds in the upper atmosphere. It had strange, the temperature was colder than expected, and so we set out to look into these features in more detail, decide which were the most important to our mission, and then to define our instrumentation so our engineers could plan what we needed in support. So this diagram shows that unlike all the other planets in the solar system, the magnetic field is, the axial tilt of the planet, it's rotating on its side rather than round like all the other ones. Magnetic field is also at a strange angle, which gives rise to a number of unusual features. We also found that ESA and NASA have both done studies and said that a mission to the outer planets is crucial to understanding the whole solar system and how it formed, so that aligned with our goals. So we came on to form our objectives, and basically it's an exploratory mission. We need to investigate everything about the system, so the interior, the atmosphere, the magnetosphere, and the satellite and ring system. So we had to go through these in detail, and I'm just going to show you the magnetosphere today, but we first of all had to define the big questions of the structure, how the magnetosphere interacts with the solar wind and dynamics, and then we had to form sub-questions and work out what measurements we needed came down, and you'll see from the various different questions we could pick out which instruments were going to be most crucial to our mission and which were going to be less so when we needed to trade off with weight and mass constraints later on. So why two spacecraft? We were looking at what we could do that would be innovative and give extra information on our big questions, and there were sort of two big alternatives that we approached, one being an orbiter and probe mission to look further into the atmosphere, and the other being a two-orbiter to investigate the magnetosphere. We opted for the second when our engineers told us it would be feasible, looked at the trade-offs, and that was our mission choice. So again, we had to look into instrumentation for missions to the outer planets. You're going to look for good heritage instruments that have been used on previous space missions. You don't want to design something completely from scratch. So that, for an example, we were looking at two instruments that they're going to build for JUICE, because by the time our mission flies, they'll be tested out.
Yeah, we were talking about the planet modes. If you look at how Saturn was researched, there's also a lot of research on the moons of Saturn.
Yes, it is one of our goals to look at the moons and so on, but we've had to bring this talk down to sort of 20 minutes, so I haven't been through all the scientific goals of all of them. But so we ended up with a model payload for the orbiter and for the slave satellite coming down to a total mass of 105 kilograms, which our engineers told us was feasible. And then I believe I hand over to Ingo to show the engineering side of our mission.
Okay, hi, my name is Ingo. I study space systems engineering in Delft, and as such I was also the systems engineer for our project, and I will present to you now the engineering solution that makes the science happen. So on this slide I first of all give you a small overview of our mission. As Jane already told you, we have two spacecraft, a master satellite, which is a big satellite that has, for instance, the main communication antenna, and a small slave satellite that is rotationally stabilized and relays data back to the main satellite. As Uranus is extremely far away, it takes us about 20 years to get there and then do 5 years of science operations. So as you can see, that's an extremely long time. And you see the mission timeline at the bottom. I will now get into a bit more detail of these individual features. So let's first talk about the interplanetary trajectory. These are some plots from orbital analysis software, and as you can see, for the very short time we did there, we managed to get quite some detailed analysis. And basically what you see here is on the left plot the inner solar system, on the right plot the outer solar system, and we do 4 planetary flybys in order to gain delta V, namely a Venus, Earth, Earth, Jupiter gravity sequence. But when we arrive at the planet, there is a choice to make a reasonable science orbit, and that turned out to be extremely difficult because there's so many different configurations you can get in. And what we came up with in the end, you see in the bottom left corner, where you actually see the orbit and the magnetic field, and as such we have an orbit that passes through the bow shock of the magnetic field in a polar orbit about the planets, and this allows us to do great science because we can measure outside and inside the magnetic field. And you see that it's a very eccentric orbit. That is mainly because then we save a lot of propellant. We can just stay in this orbit, and we do not need to use a lot of delta V, it's called, to lower the perigee, the apogee. But you already got the question about the moons, and here's an answer to that. Because what we will do with the main spacecraft, so not with the small one, is at the apogee, we actually raise the perigee, so that's the bottom, and by that make the orbits of the spacecraft intersect with the moon orbits. And that allows us to do moon flybys and do great science with the moons as well. So much for that, and as you can see, we get down to quite some detail and calculated that we would need a delta V of about 2 kilometers per second for this mission, which, if you ask me, is remarkably little for such a distant planet. But that's for now about the orbits. If you have questions, of course, you can approach us afterwards for some more detail. Now let's get to the actual spacecraft hardware design. You will see that it's kind of a crossover between the Bepi-Colombo mission, because it has 2 spacecraft, as we do, and the Cassini spacecraft. Of course, these spacecraft in reality have very different requirements than ours, but there are still elements that match. So as you can see, here's the outcome of our design, which only resulted after many iterations and trades. On the left side, you see the main spacecraft with the slave satellite stacked on top of it to the right. It's behind this gray thing because that's actually a heat shield, as I will explain in a minute. Then you have the slave satellite, which with deployed magnetometers for magnetic field measurement. And then on the right hand side, you can see that we use an Ariane 5 where we can nicely fit it into the fairing. So as you already saw, there's quite a weird thing around the slave satellite, and then that is actually a heat shield. And also we use the main antenna as a heat shield. Because you can imagine that at Uranus, because it is extremely distant from the sun, you have very low temperatures. In fact, you have something like 23 Kelvin of kinetic energy. But we also do a Venus flyby, which gets extremely close to Earth, to the sun, excuse me. And that means that you have kind of conflicting requirements in terms of thermal design there. And that is why we have to shield the slave satellite, because otherwise it would be very harmed by the close sun flyby. Just to give you an impression of the detail we went into in our study, we actually made very detailed mass budgets for both the master and the slave satellite. And we ended up with a launch mass of about 4,100 kilograms. So that is quite a lot. But Ariane 5 in its current state can launch 4,300 kilograms. So we have some margin there. And also in these numbers, those already include a 40% margin. And if we would see Ariane 5 mid-life evolution, which as you will maybe know is currently under discussion, we could even launch 5 tons. So there's a huge margin there.
And what do you use as a power source? Do you use RTG or do you use those
We are forced to use RTGs. I will also get to that in my next slide. Because in terms of mission critical items, I already told you about the thermal environment, but the second one, as you can see here, I hope you can read it, is that the solar flux that you have at Uranus is extremely little. And that is why we are dictated to use nuclear energy sources. And on the last bullet here under issues, you also see that it's a problem, because the availability of these radioisotope thermoelectric generators, as they are called, is limited in Europe. We do not have nuclear power yet, because in Europe, if you want to do anything with nuclear power, and especially in space, it's always a huge problem. But there are currently activities going on in ESA to obtain this capability within Europe. So we will see probably in the early 2030s, it unfortunately takes that long, to have nuclear power available for space applications. That means then we will be able to do our own flagship missions to the outer planets. Well, what does our mission actually do? We expect that our mission will have a Cassini-like outreach, because there's only been one flyby until now of Uranus, and the rest was based on Earth-based observations. So we expect, and it is a natural thing, that actually doing this mission, we could do great science, we could do great and pioneering exploration, and as a matter of fact, we would achieve all these firsts, namely being, in general, first orbiter about an icy giant. Secondly, study the Uranus system, which has not really been done in situ. Then it would be the first investigation of the extremely interesting atmosphere and magnetic field of Uranus, and also the first outer-planet mission with 2 orbiters. And with that, I actually already get to the end of my presentation, but I think there's still some time, because we also have a nice video to show you about the work we did, and maybe during that you can also ask some questions if you're interested. So here you actually see, first of all, the interplanetary trajectory. As you can see, we leave Earth in 2026 and approach Venus here in a few seconds. You will see it for flyby, where we gain velocity and speed up our spacecraft, basically getting free energy. And then we get into resonance orbit. So the orbits you see right now takes exactly 1 year, which means we will be at Venus at the same time again, and at Earth, and do a flyby as well. So then we get to Jupiter and get some additional speed to get to the outer solar system. But that's also already really it, because now we have to wait for about 12 years and just cruise to the outer solar system. It unfortunately takes a really long time. So we would arrive in 2045. And this is the arrival orbit we arrive in. We fly around Uranus in our first orbit. And of course we're coming from the plane of all the planets, from the ecliptic, and start flying around this planet. Next you will see how we do some science. Yeah, So as you can see, this orbit which we fly about Uranus, it takes about a month. So it's a very long one, and it's a trade-off because you have to get as close to the planet as possible to do nice observations. But unfortunately, that's not possible, so we have to do a trade-off here. As you can see here, we do some observations, some nice animation here. And yeah, in general, I just would like to give out the message to you that this is really a great summer school. We've learned a lot. And what I think is the most remarkable thing about this is that you have the interaction really between scientists and engineers, which is really something you do not learn at university at all, because everybody stays in his department, you never get into contact with the other one, and it can be a quite frustrating but also rewarding experience.
We're still talking to each other.
We're still talking, exactly. So here you can see the slave satellite, which is a spinning spacecraft, and it actually communicates with the big one, the master satellite, and the master satellite also relays the data back to Earth. Because otherwise you would have to put an antenna of 4 meters into the small satellite, and then you get really problems in terms of the mass that the spacecraft has, and also it has to fit into the launcher. And 4 meters is big, it's really big. So thank you very much for your attention, and please, we will be more than happy to answer any questions.
Yes, the secondary satellite.
Yes.
And what kind of orbit is that around Uranus? Since you say that the main satellite is in a 1 month orbit,
Right.
and the secondary one would be.
So if you would have to change the orbit of the small spacecraft, they would of course be extremely propellant expensive. So we don't do that. What we do is, in the first orbit that we do around Uranus, we release this spacecraft and give a very small boost with the main spacecraft to separate both. And as a matter of fact, then for the first 2 years, the main spacecraft would stay on exactly the same orbit and do science. And the small satellite just remains in that orbit, while after 2 years, the master spacecraft would then change its orbit. But the slave satellite does not have any active propulsion, because in terms of the mass budget, it's not possible.
Okay. How long is the communication time between Uranus and Earth?
Oh, that's very long. It's 3 hours, as far as I know. So you really cannot do any real-time work. And that's also actually a really big problem because communication between Earth and the satellite is very difficult. Because as you can imagine, if you want to make contact with the spacecraft and you point your 72-meter antenna at the spacecraft, you first want to send a signal there, and then the spacecraft sends it back in order to confirm that you have made contact. But that already takes you 6 hours. So, and the Earth is rotating, and as you can imagine, if we are on one hemisphere, on one half of the planet, we only have 12 hours to communicate. So actually you need 6 hours to establish communication, and then you have maybe 2 hours for downlinking data. And that's quite tricky, but possible, because with Cassini, for instance, they also do that.
What's your data rate for download?
I have the link budget, but it's not much. We can download about 2 gigabits per month only.
So how are you doing the communication with the slave satellites in terms of their transferring data? What's the buffering like in the main orbiter in terms of transferring data from the slave to that, and then it's got to not
that's how it works. Exactly. So you have 2 low gain antennas actually, which just transmit omnidirectionally in outer space. Omni, yeah. But we made the calculations possible. And as a matter of fact, there's also no other way for the slave satellite but using a small ITG on that one. So there is some margin on the power, and we can actually do the communication. It's yeah. Can pause here. So, any more questions, or do you want to say something here?
In which stage is that now? Is that now a proposal, or is that mission going to be launched?
This mission is this mission was selected as the best mission of the workshop, and as a next step we will meet in December again with a few tutors and work out for a week in more detail how we can implement this mission, and from that we will do the publication in a journal to present this kind of concept, because it's actually it has not been studied extensively yet. And as Jane told you, there's a very, actually with the NASA at the moment, there is some priority to go to the outer solar system, especially to Uranus, because it's still closer than Neptune, to do such a mission. It would probably not look like this, but we think that we can do some input to the discussion and maybe hope that there will be some momentum in order to fly such a mission. Because we think that the really great discoveries can be made, and the major selling point of this is actually that we don't know yet what we will find at Uranus. And that's exactly like with the Cassini. We've made so many discoveries, it's remarkable.
But the cloud surface of Uranus is very visually dulled.
Ah, that's not true. That was
relative to Cassini and what Cassini can generate.
Okay, that is, yeah. But it was believed in the beginning, especially from the Voyager flyby, that it's just a blue blob.
No, it's not.
No, it's not. Now we had an expert on cloud tracking and all these kind of things in our team, and he actually got quite excited about the science he could do there. So there's a lot to do.
We also have a poster downstairs that you may have seen sort of around the back of the main room. Do feel free to look at that and ask us questions.
Yes. Otherwise, I think we can even finish the session in time, so you can get to the next one in time as well. Thank you very much.